We have prepared a series of short films to help you understand the basic principles of continuous flow gas lift. Continuous flow gas lift is used to increase the production from flowing wells or to obtain production from wells that otherwise would not produce. The equipment for gas lifting a well includes gas lift valves, such as you see here. For use in a well, each gas lift valve is screwed onto a mandrel. The mandrel with its valve is then screwed into the tubing. And finally, the tubing with its gas lift valves is run into the hole. Let's listen to Stan Brown, one of McMurray's engineers, as he tells us about the model that he will use to explain gas lift.
To explain the principles of gas lift, this series of films will use the physical model we see here. This model was designed and built by McMurray to simulate the performance of a producing well over a wide range of operating conditions. This introductory film has two objectives. First, to acquaint you with the model and with a related graph, which are the tools we will use to study gas lift. And second, to explain what is meant by the term pressure gradient. Let's move on to our first objective and examine the model and see how it simulates an actual well. As we can see, the model is producing in a natural flowing state, and all of the energy is being supplied from the reservoir. On the surface, we have input gas that delivers high pressure gas to the wellhead. We have also an adjustable input control valve with which we can control the volume of gas that is injected into the casing tubing annulus. Since the well is in a natural flowing condition, lift gas is not required, and this valve is closed. Plastic tubes simulate the casing and tubing of an actual well, and the well is producing up the tubing. We also have a flow line, a wing valve, and a separator. This surface gauge reads input pressure and is the lift gas pressure available at the wellhead. This gauge reads flowing wellhead pressure. Below the surface, we have three gas lift valves located at the simulated depths of 1,300 feet, 1,990 feet, and 2,350 feet. These valves are designated respectively as valves number 1, number 2, and number 3. Our well is perforated at a depth of 2,740 feet, and a packer is set above the perforations. This gauge reads the pressure in the wellbore opposite the perforations and is the bottom hole pressure of the well in either the flowing or the static condition. The gauges located at each gas lift valve read pressure in the tubing at the depth of that particular gas lift valve. Notice that this is tubing pressure. It is not the pressure in the casing tubing annulus. In a moment, you will be able to see how these pressure readings can be used to draw a graph that will give us the pressure conditions in the well. The model has meters to give us a reading of 3 required flow rates: input gas in thousands of cubic feet per day, formation gas in thousands of cubic feet per day, and formation liquid in barrels per day. In this model, the liquid meter measures only formation liquid. It does not measure the liquid produced from the casing tubing annulus during unloading operations. The gas lift designer must be capable of translating a well's flow performance to a graph for analysis. So we need to look at the form of this graph. Note that the horizontal axis represents pressure in pounds per square inch gauge, and the vertical axis represents depth in feet. In the examples we will use, the gas lift valve locations and the depth of perforations will not vary, and so they are plotted permanently on the graph. Notice also that the vertical scale of the model and of the graph are the same. We have become acquainted with the physical aspects of the well model and with the graph that we will use. Now, let's move on to our second objective and study the well model in its flowing condition to learn what is meant by the term pressure gradient. We are producing 1,000 barrels of liquid per day and 400,000 cubic feet of gas per day from the reservoir. Our flowing wellhead pressure is 200 pounds per square inch. The flowing tubing pressure at the 1,300-foot level is 270 pounds per square inch. At 1,990 feet, the pressure is 335 pounds. At 2,350 feet, the pressure is 380 pounds. The flowing bottom hole pressure is 430 pounds per square inch. When we connect the 5 pressure points together, we obtain the green line that shows the flowing pressure distribution in the tubing. We call this line the flowing gradient curve for the given set of conditions. In this instance, the conditions are 1,000 barrels of liquid per day and 400,000 cubic feet of gas per day. This represents a gas to liquid ratio of 400 cubic feet per barrel. The word gradient simply means rate of change. Hence, a flowing gradient curve is a curve showing the change in tubing pressure with well depth as a well is flowing. Now, suppose the well conditions should change. Instead of producing at a 400 cubic feet per barrel ratio, suppose the well is now producing at a 235 cubic feet per barrel ratio. Our new production would be 850 barrels of total fluid per day and 200,000 cubic feet of gas per day. Let's see how these changes affect the pressure gradient in the well. Our flowing bottom hole pressure has increased from 430 pounds to 515 pounds per square inch. Now, proceeding upwards, the flowing tubing pressure at the 2,350-foot level has increased to 450 pounds. At the 1,990-foot level, it has increased to 400 pounds. At the 1,300-foot level, it has increased to 315 pounds, and our flowing wellhead pressure has declined to 180 pounds per square inch. Connecting the points to obtain the black line, we have the flowing gradient curve for the new set of conditions. 850 barrels per day with 200,000 cubic feet of gas. Comparing the green line and the black line lets us see easily the changes that have occurred in the flowing gradient curve with a change in well conditions. We have covered both of our objectives, so now let's summarize. 1. The well model simulates the behavior of an actual well, and a graph of pressure versus depth can be used to study well performance. 2. Pressure gradient means a change of pressure with well depth. Pressure gradients change as well conditions change and are very useful in studying well performance.